Barrows, a physics AI engineers and developer from San Paulo, Brazil, who brings a valuable international exposure and technical insights to these sessions. I am warmly welcome our panelist and moderator, Engineer Himanshu Bhatt, partner of Maxell Design LPP, who expertise and guidance will enrich today's discussions. I would like to place on record my sincere appreciation to the IEA South Gujarat Local Center, Dr. Kingsuk, and the organizing team for their delight, diligent efforts in customizing the successfully arranging this approved continuing professional development program. Such initiatives truly strengthen the IEI missions of advancing engineering knowledge and serving the nations. I encourage all the participants to actively engage, ask questions, and make the most of these interactive learning opportunities. I am confident that today's third webinar in this series will continue the momentum of excellence set by the earlier sessions and provide the valuable technical insight. Once again, I extend my warm welcome to everyone and wish webinar great success. Thank you and have a highly informative sessions ahead.
Thank you, sir, for your kind words of wisdom. May I now request Engineer Himanshu D. Bhatt, the moderator of this session, to kindly brief about the theme and for today event, sir, please.
So, good evening, all. You have to pardon me today for my voice. Actually, today morning only I got some thing in my throat, and now it has added a lot of bars to my voice. So, you have to manage with that. I'll share my screen. Is the screen visible?
Yes, sir. Yes, sir.
Yes. So, welcome again, all the participants, the speaker, and our chairman. This seminar today we are going to discuss about PiNNeAPPle. It is a platform where we can
তো যে
do
একটা
engineering
লিঙ্ক কাজ
simulations
করছে না
using physics where AI. We'll talk about that later. So, what is open source? That we'll start with first. So, open source technology, because this platform is open source. So, what is open source? We will understand that. When we talk about free open source, it is not a free software. It is not just a free software. It can be a free software, but it comes with lot of additional benefits. These things we have discussed in our past two webinars. So I'll just quickly move through that. So open source basically has its source code available publicly. That is called open source. So anybody can study, modify, redistribute the code under specific licenses. But if you are a user of the open source tools, you don't need to worry about any of the licenses. You just uh, download the codes and start using. Are the open source software reliable? This is a question which we have been asking and trying to get answered in our this webinar series. Today is the third session. So you know that we have a Android phones, many examples of open source now. We studied two softwares also in past two webinars which are useful for engineering work. So the open source struggles, we are trying to come out of that, and we are trying to break the constraints of these struggles. Coming to today's session, this is a QR code for the GitHub repository of our today's topic, which is PiNNeAPPle platform. So you can scan this QR code and you can study the complete source code, which we will be talking in this webinar. The project philosophy is very attractive, and it is PiNNeAPPle is not just a single model or method, it is a platform designed to let physical data, geometry, equations, and learning systems interact cleanly, reproducibly, and at scale. This is very important when it comes to AI, that things needs to be reproducible when we talk about engineering application. So with this, I again welcome and I'll introduce our today's speaker, Mr. Jan Barros. He is from Brazil, São Paulo. He is a data scientist and AI engineer specializing in physics-informed machine learning and scientific AI systems. He is the creator of PiNNeAPPle, which is our today's topic for development, training, benchmarking, and deployment of PINs. What is PINs? PINs is physics-informed neural networks, and hybrid physics AI models. He is also organizer of international communities focused on physics AI for next generation simulations. The QR code is about his LinkedIn profile. So if you want to get connected to him, you can just scan the QR code and you can get in touch with Mr. Jan Barros. So now with this, over to you, Mr. Jan Barros.
Thank you so much, everyone. Are you listening to me? Are you able to listen my microphone?
Yes.
Okay, cool. So thank you so much for this amazing introduction. Before going to the presentation, I'm going to talk a little bit about myself and a little bit about open source technology. So my name is Jan. Started on this field some years ago with a single problem in my mind. It was how can we predict El Nino, hurricanes, tsunamis, like weather forecasting, extreme phenomena. In physics, we call these complex phenomena. And I was thinking because I came from Northeast Brazil, where it's a place that people lives a lot about farm and they plant a lot of different cultures, different plants. It's really important for our economy in Northeast Brazil, especially for small farmers and people that lives only for this. So in my mind, that came like if something really weird happens to the weather, like the rain stops or the rain becomes too higher, how those people can plant different things, how can they survive because they depend on it. So this is why I discover about complex systems, discover about El Nino, and start studying about physics informed neural networks. This came for the YouTube channel from Professor Steve Brunto, which I really encourage everyone that it's interested in this field to go deeper. There are amazing topics about physics informed neural networks, about neural operators, deep net. So it's a really solid concept for everyone to study. I'm going to share my screen. Okay. Are you seeing my screen?
Yes, the screen is visible.
Okay. So PiNNeAPPle, as I said before, came as an idea for me like last year. Me and two friends, Enrico Schiassi and Lorenzo Grazzi, we came with the main idea that was we were seeing some startups, some companies doing some effort on simulation tools with AI. So we saw a lot of products, a lot of development on CFD things, and most part of them were only like for startups or paying products or some process that you need to pay for using. And I received a lot of messages on my LinkedIn about people wanted to learn about pins, want to learn and how to build their own models for their own problems. And I was thinking, okay, so there's a lot of interest in the community for everyone for understanding the topics, for building their own models, for testing. And at that moment, I was really involved on computer computer vision problems. And in computer vision, we have the Ultralytics platform. When we go for LLMs, we have the Hugging Face platform. And for those who doesn't know exactly what those platforms are, they have different models for different problems in that specific field. So, for example, in ultralytics, you came for computer vision, and you have some problems like classification problems. You have some different models, different problems specifically, and you can download and use and test different models for the same problem. So you can say, okay, this architecture, this model is good for dogs classification. This problem is good for counting the number of machines in a yard, for example. So you can test different different models. You can download it, and you can integrate this into your products. But when when we came for physics AI, that it started to have a boom last year, we didn't have specifically the same place where not all of the things, but the most part of the things for that field would be put there, and people could check and create and test and develop. So this is why PiNNeAPPle was born. And the first principle was to have this way to democratize physics AI. This is what we had in mind in the first moment. When we had that feeling, we start to develop some, I would say, the first pipeline that we have for PiNNeAPPle. And this was last year, so it evolved a lot. Right now we have 76 different architectures for models, which you can use for training and test your own physics AI model. So you can use graph neural networks, you can use LSTMs, you can use MLPs models. There are several architectures. We are going to talk a little bit more about that. We started with some, if I'm not wrong, it was 5 modules in the beginning. That was what we had as the core. So how can we came from a symbolic equation, like a natural language equation, and turn this into a loss function for training a neural network? Because this is the main concept about physics informed neural networks. You add physics constraints inside of the loss functions. But this can be quite hard, this can be quite complex depending of the problem that we are working. So how can we easily help engineers for adding this for their own training their own physics AI models? This was the first core of the PiNNeAPPle. But then we evolved for more modules. Then we on the last months, we were seeing that we can solve some specific problems, and we can put there for everyone that if you want to solve that problem and it's already solved by PiNNeAPPle, you just can load the problem and you can use this. So we create the presets for some specific problems. We also have some presets for PDEs and with their boundary conditions, initial conditions. This is something that quite evolved for PiNNeAPPle in the beginning. At the end of the presentation, I'm going to talk more about what are the plans for the development on PiNNeAPPle. And this is important because we were discussing that this is an open source framework. And being open source means that everyone can contribute. So you had the repository link at the beginning of the presentation. Feel free to open there, check, understanding, and add some issues, add some contributions. Everyone is are welcome to contribute on the framework. This is why open source works, because everyone tries to build something better for the community. It's not about me, it's not about Henry, it's not about Lorenzo doing the things, but it's about the community working and build things for the field that we think should be. This is the way that we think the science should be open for everyone and everyone contributing and collaborating. It's not should be only specific for some company or this kind of thing. So about the motivation, again, about the building PiNNeAPPle, we saw, as I was saying, some fragmentation in physics for machine learning field. So we saw some frameworks and some people doing some specific research. For example, we have the DeepXDE was probably, if I'm not wrong, was the first package in Python for pins, and we use a lot on that moment. Then we had some months later the CNN, which is a TensorFlow interface. It's a Keras TensorFlow. And we also had what we call in the past, it was physics modulus. Right now it's physics NeMo. Probably it's the most common used and famous framework for physics and for neural networks, especially because they had a lot of integration with the NVIDIA infrastructure, which helps a lot for training heavy models, testing, and when you see a lot of the applications for the startups and the companies, most of them are using the physics NeMo. But the main concepts were really isolated from each other. They were not talking about the main process for building the engineer problems. So we solve the equations, we generate data, we train a model, but this was not the whole pipeline about engineer tasks using AI. So we need to understand what is the problem. We need to grab and extract the equations. We need to understand the physics before go there. So we had a system design part. We are going to discuss more about this, but those are some problems that we were facing and we were realizing that exists on the ecosystem about physics for machine learning. So another problems that we have, we need to re-implement loss functions from scratch for every new problem. So how can we easily build a new loss function for a new problem? This is something that wasn't solved in the past. So we create something for this. The collocation points is something that it's really important for training the neural networks in pins. And we sometimes need to do this collocation sampling from scratch either. So how can we easily manage those strategies for collocation points? How can we balance the loss components? So we have the data loss, we have the boundary conditions loss, we have the PDE loss. How can we work better for them without having competition between the losses? So this is a problem that we face when you start training pins. We have a lot of convergency problems because of this. The laws are always competing. So the model becomes start to being confused, and this is a problem for convergency. Again, how can we do this part for inference and deployment? The physics NeMo works a lot on this, so we also need to build something about this part. And again, we have a lot of different tools, and all of them connect, including the numerical solvers tools that we already have. So building something that use AI doesn't mean that we don't need to use the ANSYS, Siemens, NVIDIA platforms. This is the opposite that about what we are building. We are building something that can connect with NVIDIA, can connect with Abacus, can connect with OpenFOAM, can connect with different technologies and frameworks. So everyone can test and go in the best direction that they think it's enough for solving their own problems. One specific thing, we can see a lot of approaches for digital twins when we talk about scientific machine learning fields. So we are building some tools that can help this digital twins integration inside of PiNNeAPPle. A little bit more about the last version that was released for PiNNeAPPle. It was the version 0.4. We have the symbolic problem specification, which we have discussed before. We have some simplified geometry construction. So if we want to build some geometry, 3D geometry, 3D STL or BJ file. It's not the CAD file, but it's a representation of the CAD file. If we want to build easily some geometries, we can do for the simple one, but for complex geometries, PiNNeAPPle doesn't support yet the easily construction for it. But from the geometry with PiNNeAPPle, we can generate the mesh, generate the collocation points inside of the mesh, so we can integrate this easily just from an STL file, for example. We have the physics constraint training, we have the physical consistency validation, and we also added a real-time digital twin deployment, which can connect with real sensors. It's like the PiNNeAPPle already can build the server, the API, and there is a module only for this, so you can create easily your models, upload that for the server, and with the server you can integrate with your own APIs, with the data, real data for generating inference and those processes. So again, we have those information about PiNNeAPPle. And for building the platform, we had four design principles. One, it's the problem first design, and it's what we were discussing in the beginning. Before going for the training part, before going for the simulation part, we need to understand the problem, and all of the all of the information, all of the concepts about the framework, the PiNNeAPPle framework came for the we call this problem spec. Basically, you define all of the informations about your problem. It's a JSON format, and you can use this for easily run the simulations and go for the next steps of the problem. But this needs to be done first. So you need to create and define your problem. If you have some issues about creating a problem, you don't know exactly what are the equations, what are the physics problems that we want to solve. There is some modules that integrates with LLMs. Right now, we are only integrating with Gemini, but we can expand this in the future. But you can integrate with your LLMs, and this can help you to create your own problem spec part of the things for running the pipelines. So it has a full life cycle coverage. So we came for the problem design, then we passed for the geometry. Notice that the geometry part is not it's not an obligation, but most part of engineer problems, industrial problems, we have the geometry, the 3D geometry. But if we don't have, we can use the pipeline in the same way. But so we came for the problem. We understand the physics. We understand the problems. We have the geometry. We use that for generating the data set, running some simulations, numerical simulations. Then after we have the simulation with the geometry and the mesh, we can then train a model using GPU or not, if we don't want to use GPUs. It works without GPUs either. And after we trained the model, we added a module recently that it's uncertainty quantification, which is basically you took the results of the model and you understand if the model is right or not. It can be right or not. After that, you can apply for digital twins and creating your APIs or doing the things that you want to do. One thing that we can see here is we don't have yet a module for visualization, for data visualization. I'm not sure if I'm going to add inside of PiNNeAPPle or if we think it's better for just having some connectors with some visualization tools like ParaView, for example, or I don't know. I'm not sure about this, but feel free to give your insights or suggestions about this. But we want to build in the future some visualization module for PiNNeAPPle, but we don't have this yet. We have 76 different models from 13 families. So we have PINs models, we have time series models, we have graph neural networks models, convolutional neural networks models. Those architectures we have inside of the pipeline. And this is really important because we can use those different architectures for the same problem, for understanding if we have a specific problem, it's better for us using an LSTM or using a convolutional neural network. It's better for us using a graph neural network or a pure simple vanilla PIN. So you can change the architectures easily. So it's the architecture of PiNNeAPPle. It's agnostic of model architecture. You can change easily the architectures and test different models easily. And the outputs, the models, they are ready for production. So we have some AMP mixed precision process. We have distribution data in parallel. So we have adapted for this. We have exports for TensorRT, for ONNX. So you can easily connect and generate the best inference process. So it's ready for production. We have some ZAR streaming data loaders, which are faster than using NumPy or other platforms and frameworks and formats of data. And we also have this digital twin runtime that it's a server that is ready for running. So we are working on this process of the parts of PiNNeAPPle. Talking about the modules that we have right now for the framework. So we divide in 5 layers the architecture of for solving the physics AI problem. So we have the problem definition, we have the data preparation, we have the model and loss creation generation, the training part, and the post-training and deployment part. So for problem definition, we have two main modules. One is the PiNNeAPPle environment, which have a lot of presets for engineer problems, equations, boundary conditions, initial conditions. We can use that. And we have the problem design, which is the module for connection with LLMs that we discussed before. For the data preparation, we have PiNNeAPPle data, which is basically what helps you to generate your collocation points, generate your data set itself for a physics format. We have the PiNNeAPPle geom, which is for working with the geometry, and we have the PiNNeAPPle solvers, which we have some integrations. I didn't test too much, but so I encourage you to go there and break the things. So we broke the thing, so we can fix that. But we have created some wrappers for integrating with OpenFOAM, with Phoenix for structural mechanics, and we have some FEM, FVM, and FDM solvers using MATLAB and Python, all integrating inside of PiNNeAPPle. But I didn't test too much about them. For model and laws, we have the PiNNeAPPle models, which is we have the zoo architectures of models, which we can select for training the model, for training the physics AI models. And this is important because on PiNNeAPPle models, we don't have only the physics models. We can use normal, regular architectures that don't have the loss functions inside of it. And we also have the PiNNeAPPle PIN modules, which allows users for creating their own customized loss functions using the symbolic representation. We have the training modules, which is PiNNeAPPle train for training itself the model. So it connects the models with the pins, the loss functions of the pins. So we can use this for training inside of the PiNNeAPPle train model. We added last week or 2 weeks ago, the PiNNeAPPle transfer, which is a module that allow user for having the transfer learning between physics models that he already have used. And we also had the PiNNeAPPle Meta, which is a module for meta learning process, which you can connect with the transfer learning and you can connect with the train model. Finally, with the post-training and deploy, we have the inference module. We have the uncertainty quantification, which is the UKey module. We have the validate module, digital twin, the serve, which is the server itself that we call for digital twins, the export module for get the model and export for different formats as SOX and N, for example. And we have the PiNNeAPPle Arena, which is a easily way for us to helping the users to test in different architectures in a YAML format. So you can select the architectures, you can select the models, and you can train the things. I don't know for the hosts if we need to allow people to give some questions right now or have a break, or if I can continue. What do you have in mind?
Yeah. So most of our audience are mechanical engineers, and they would
Okay.
be more interested in practical usage of this. They would not be much interested in the development part of it.
Okay,
So you can put your talk on that series. And
okay,
Kishore says if we can allow the chat session so people can put their questions if there are, so we can make it interactive.
cool, great. Okay, so keep going on. I will be a little bit quick on the development part. So here's how can we create the abstraction of the problem for using the problem spec, the PiNNeAPPle environment. We have some preset equations like Burgess, Poisson equation, we added on the last weeks von Mises stress strain analysis, crash mechanics analysis. You can also import there. Then you create the spec on this format, and you can use this for consuming on the less on the other parts of the problems that of the pipeline for PiNNeAPPle that we have. So for the presets problem that we already have, we already have built 5 problems for 5 domains. So we have flow mechanics, which is CFD. We have some examples using PiNNeAPPle that are already created, and you can import here like easily like this. For Navier-Stokes 2D and 3D incompressible, Darcy flow, Burgers equation. For heat and mass transfer, you can use steady and transient 1D, 2D, and 3D. We have a React diffusion problem already inside of the package. For structural mechanics, we have plane stress, von Mises, drill pipe torsion, thermoelasticity problems, and we are adding, I don't know if today or this week, some crash analysis for the pipeline. For wave phenomena, we have Helmholtz equation and Clyde-Gordon equations. And for other different domains that can be applicable, we have in finance, we have Black-Scholes equation. Epidemiology, we have SIR equation. We have drug diffusion, and we have some process for astrophysics. You can check there and understanding more about what we can use for that. About the PiNNeAPPle data model that we have, it's a way that we can organize better the data into physics data set. So it has already some integrations with NASA open data sets. So you can extract from real data that can be, right now we have the integration with NASA, but you can integrate any kind of data set. You just define the fields, define the coordinates that if you want to, you can put the independent and dependent variables here, and you can create this format of data that you can reuse easily and faster in the future. So if you have like a different data set that has, for example, dimensions properties, has material properties, but they are all without any organization. So you have different sources and you want to connect them, you can create a unified data set that has the physics constraints inside of it. For the collocation sampling, which is important for training the physics AI model, you need to define the strategy that you want to use for the collocation sampling. So you can use uniform random, Latin hypercube, that it's one of the most used way for it's one of the most used techniques for collocation sampling. We have Sobol sequence and we have adaptive sequence here either. So you can use all of them. For the physics laws compilation, how can we create our physics laws for training the models? So basically, you create another spec, which is the core for PiNNeAPPle. It's using the specs. So you pass the pin problem spec. You put your equation here. So it's a PDE residuals. You put here, for example, it's the same way that we use symbolic equation. So you use here derivative of u in function of t plus ut. So it's the main equation. So it would be something like ut plus u. This is the equation here. So the independent variables here are t, and dependent variables are u, and you add the loss weights here, which for the PDE you are adding a loss that it's 1. What is this loss weight? When you train a physics-informed neural network, as you can see here, you have the weight for the collocation points. For the collocation points are the physics loss here. We have the weights for the boundary conditions, initial conditions, and the data itself. So when you add the loss for the PDE as 1, you're saying that the double here is 1. So basically what happens? It automatically creates the loss function for you using those rules specifically. So if you pass, for example, the derivative of u and t, you use the gradient of PyTorch because it was main constructed built using PyTorch. You have Jacobian integration, Laplacian, divergency, and time derivative. So you can use those things either for creating your equations and process. For training the models itself, for loading the models in physics, in PiNNeAPPle, you PP here, it's the PiNNeAPPle, so you import PiNNeAPPle as PP. You can list the models that we have there. You can list the models from one specifically family, and you can load the model using the build model. You put the name of the model and the parameters for building the models. Here's one example using Fourier neural operators. But we have 13 families and 76 models. So things, neural operators, graph neural networks, transformers, autoencoders models, continuous time models, recurrent, reduced order models, and reservoir kernel models, and some benchmarks here. So you can load easily any kind of those architectures using PiNNeAPPle. For the training infrastructure that we have built for PiNNeAPPle, we have 4 automatic loss weight schedulers. So you can use these for regularize and optimize the loss between inside of the training. So you can use those the gradient norm balancer. You can use the NTQ weight balancer, the self-adaptative weights, and the loss ratio balancer. You can also use some features for GPU acceleration. So it's not only integrating with GPU, but you can use gradient checkpoint. You can use the torch compile. You can use the AMP, and you can use the DDP. So those techniques, those features you can use for HPC process. We were building, thinking about this. We have the models for uncertainty quantification, as we were saying. So you generate the prediction using the U-key predict. So you pass the model, you pass the data set, you pass the method for quantificate the uncertainty of your training, your model train. And you can use MC dropout, you can use ensemble U-key and conformal prediction. This is important for validating your training after the training itself. We are creating, but it's not so robust right now, the meta learning process for some PDE families. So I will skip a little bit about this, but we already have some. It's not so robust. So you have some questions?
Yeah. So now we have around 15-20 minutes left. So if we can put up some whatever we are discussing, like the PD families and the model training and all, if we can have some example of that, that would be interesting to know in this last 15 minutes.
Yeah, let me check one here. I don't have the examples run, but I can share something for you. Just a second. Just let me open. Check if it's there on GitHub. Let's see. I'm going to share another screen with you. Just a second. Have you seen my screen? Okay, my screen is okay. So on PiNNeAPPle package, we have the examples folder, which you can check a lot of different examples. And I'm going to show you how can we load a 3D geometry, and we can train here is a heat equation model, but you can adapt for flow mechanics problems. I don't have an example here, but we have von Mises equations and Hooke's laws equations inside of the package. But for being faster, I'm going to give this example for you, for understanding how you can use this for adapting for your problem. So basically, we import the package for PiNNeAPPle. We import the load STL, which you can load your 3D geometry for running some tests for depending of your problem. Here you load the STL file, and you already generate the mesh for it. So you not only just read the 3D geometry, but you already create the mesh file here. You can correct the mesh here using the repair mesh, and you can simplify it if you want to. Then after you load the geometry, you generate the mesh for the geometry. You generate the collocation points here. So we are using the sample surface points. You pass the mesh here, and it creates your collocation points here. Then you can define your equations. So basically, you came for the geometry, you generate the mesh, you generate the collocation points, then you pass these for the physical sample, which will be your loss, physical loss here. So you pass the state of the variables, you pass the geometry, the domain here. So it's a point cloud domain. Then you load your data set, you build your architecture. What is important here, you can load the architectures from PiNNeAPPle, or you can build your own neural network from scratch here. Then you create your loss. So here we are not adding the physics loss, but you can add, just putting these, as we showed before, you create your loss spec and you add here. Then you can load the trainer for PiNNeAPPle, passing the model, passing the loss function and the metrics. And you can, you need to create the training configuration, then you can train it. So it's really easy to run the pipelines. If I'm not wrong, I have some visual examples here. Let me check. I didn't prepare this for this presentation, but I think I have some examples here. Let me check.
I can understand because being open source platform, we are more keen to see how it works. But obviously, as a developer,
Yeah,
you need to see how the code, how it works behind
yeah.
the screen and how the codes are there.
Oh, I have this one. This is cool.
Okay.
I don't know if the code is here. Yeah, this is one example for a real pipe or a surrogate model. So this is structural mechanics. I think it can be good for you guys using for mechanical engineer. So basically, drill pipe, it's a connection that we have a lot on oil gas industry when we need to connect different pieces. So and we need to analyze the damage in the thread for after running and connecting the pieces. So the problem description here, we have axial load, we have torque, we have bending momentum and contact pressure. Those are the parameters we have here. And the equation we are using is von Mises stress, which I was saying to you, which we can use for identify wear prone regions. So basically, this is the main problem we are using. The pipeline we use for this problem is we came for geometry. We load the geometry with the PiNNeAPPle geometry. We generate the numerical data set running a solver. In this case, we use the Phoenix solver. The Phoenix, you can load with the Phoenix bridge for PiNNeAPPle solvers, but it's important that you can only use for Linux setup. So if you try to run this on Windows, probably will crash because you need to install some things, and I'm not sure if you can install Phoenix using Windows. But if you load on this example on Linux, it will works a lot. Then the Phoenix solver generates the stress field for you. You create a data set with the stress fields and the collocation points. Then you can train a physics-informed neural networks. You can predict the wear field for this problem. And you can generate wear visualization. So we generate the data using the PiNNeAPPle inference, and then we plot the data. And then you can use and connect this for a digital twin, for example. So for running this, you need the PiNNeAPPle for sure, the Phoenix for integrating with the solver, the Gmesh for, I think the PiNNeAPPle already installs the Gmesh, and you can use the PyVista for the 3D visualization. So this is the definition of the problem. You can load the preset for drill pipe here. This is one example. You can have pipe torsion. What is changed from one to the other? They are the same, if I'm not wrong. Yeah, okay. So you can load the, yeah.
Yeah, one question here. This Phoenix you used as solver. Is it hard bounded, or can we use something other like Calculix or something else?
Yeah, you can use the Calculix. You can use any kind of solver for structural mechanics. It's not a problem. You just need to here. I've started to create a wrapper with Calculix, but I didn't finish. So the thing is like you need to generate another part, another script that can generate the data using Calculix. Then you just pass the data for the pipeline. It's the same thing, but it doesn't do so simple as we have with the Phoenix here. So after here we are running the Phoenix. So we load the Phoenix bridge. We set some parameters. We need to define the torques, axial forces. Here is the script to be run on Phoenix. Then you need to run this on Linux, as I was saying. You can create your data set after you generate the part. So this step 2 here, as you said, you can replace this for the calculus part. So you need to define the problem, but then you can, here we are solving with Phoenix, but you can solve with calculus or any kind of solver. Then you pass the data set here for training, for generating the data set. You pass the data for that we had there. So we load from Phoenix, but you can load from other sources. You just need to there is no easily adaptation right now in PiNNeAPPle for this part, but you can adapt here. We do a normalization of the data. Then we load the model that we want to use. Here we are using a simple neural network. We load the data set, then we train the model here. It's another example here. You can use the DeepNet for doing the same process. And here you can, I don't know if it's plotted, I didn't run this, but you can plot the results for, yeah, I didn't put the results here. It's not, the PNG is not here. But this is the way that you can run a drill pipe example. For example, it's not the same problem that you are working problem, but you can use this for adapting for mechanical engineer and this kind of process. So here's one example that we have. Just let me check if I have some visualization data here for any kind of example. We have the end-to-end.
Okay, in the
Yeah,
meantime, you look at that. One more question. Do we have
yeah.
any GUI for this PiNNeAPPle platform, or it just runs on the CLI?
What is the question?
Do we have any GUI for this PiNNeAPPle, or it runs just on the CLI code?
Oh, okay. Yeah. Only right now we only have the CLI connection, but it's something that I'm planning to build. I would like to build something visual like
Okay.
the Hugging Face or this kind of thing, but it's too much work for one people, so one person. So I didn't finish this part yet. Yeah. Okay. So this is what
Are
I've
your
prepared for
device?
you today. If anyone has questions, feel free.
Yeah. So, do we have any questions from participants? Since you can just check if somebody has raised a hand or not.
Yeah, I think there is someone. It's Prashant still. He's with his hands raised.
Hello, Kichu sir.
Yes, sir. The chat box is not fully active. I'm facing some problems, sir. We can't communicate with the
No problem.
participants.
Okay, can we unmute the person who has raised the hand so that we can take his
Uh,
question?
I'm trying to make it. Who has raised the Prashant, na?
Yeah, it's Prashant still.
Prashant. Ah, attend. Ah, Prashant still allowed to talk. Mr. Prashant?
Yeah. Can you hear me?
Yes, yes, yes.
Yeah,
Please, sir, please.
Yeah, thank you so much. Thank you so much. It was a very nice presentation, but it was like kind of a CLI kind of a thing. It's not a GUI. I'm already
yeah,
working in some predictive maintenance using some LLM-based applications. Right now, I'm facing a very important disrespect of LLM as being it hallucinates. So
yeah,
how can we incorporate the problem of being hallucinations in the LLM?
Devai.
I have done RAG also, retrieval
yeah,
augmented generation, and I am also working on the CRAG, corrected retrieval augmented generation. So can you just
yeah,
elaborate on my query? Thank you so much.
yeah, sure. Uh, we have two different fields here. When we use LLMs, we can use the LLMs for generate code, for example. This is probably how you can use for not hallucinating on physics informed field. I'm not a huge fan of using LLMs for, yeah, I depending of the process. But what I can say is you can have the concepts about the physics problems. So I would say with what we have on PiNNeAPPle, that it's the boundary conditions, initial conditions, the geometry, and the physics equations, the symbolic physics equation for the problem, and the geometry. You can pass this for the LLMs as probably a context or a data for the RAG if you want to do this. And you can ask for creating a physics informed neural network or this kind of thing. There might be some issues. The first one, it's depending of the architecture, it probably won't work too much because pins are not something too much being using on the industry and research. So probably the LLM doesn't have too much knowledge about this. So you probably need to add also some knowledge about the architectures or researches about pins. This is something that can help. The other part of the problem is how can we pass the geometry inside of the LLMs for the LLMs understanding the things. So this is not an easy thing because if we only pass the boundary regions, boundary points of the geometry, if it's a complex geometry, we don't pass the whole thing for the LLM. But if it's a too complex geometry, if we pass the whole file for the LLM as a text, it could be really, really huge, the file. So I would say the main concept is we need to pass those informations. We need to pass the geometry. We need to pass the problems conditions, like the boundary initial conditions and the PDEs, for example. And we need to give this context about the main architectures that works, uh, how to build a pin, and the geometry part. But how can we put the geometry part? It's a challenge. I don't have the answer for this, and this is why I'm not using LLMs for building this part of the process. But it's one thing that can be, I think it's one thing that we need to study. How can we optimize the geometry inputs for LLMs? I don't know, but it's something that you can take a look at this.
Fine. So, to conclude this session, I think, hello, am I audible? Yeah. So, to conclude this session, I thank our today's speaker, Mr. Jan Barros, for giving this insightful information about pins. We hope that there is a nice GUI in the near future so that we can all utilize it in a much better way. But
Yeah,
we could
definitely.
understand it was nice and enriching to see how the formulas, the physics is built into the code behind the software and how it works
Yeah.
as physics informed AI and LLM training. So thank you once again, and take this opportunity to thank our chairman, Dr. Nilaj Kumar Deshmukh, for being present today to encourage us and keep doing such more sessions, informative sessions. And I thank Institute of Engineers India for providing this wonderful platform to connect with all engineers with common interests so that we can share their knowledge with each other and grow. Thank you all. Have a good night.
Thank you so much, guys. Have a nice